Welcome. We are looking at solution models and trying to understand them by using GNU Octave. We looked at ideal solution. Let us look at regular solution model. What does the regular solution expression say? Regular solution expression says that delta G of mixing is nothing but omega x into 1 minus x. So, that is the enthalpy part, and this is the regular solution parameter, plus RT, the entropy expression is as in the ideal solution model. So, that is what the approximation was, that the mixing is random as far as entropy calculation is concerned. So, x ln x plus 1 minus x ln 1 minus x. As usual, let us do the non-dimensionalization. So, I am looking at delta G by RT is equal to some omega by RT x 1 minus x plus x on x plus 1 minus x logarithm of 1 minus x. Okay. So, let us call this omega by RT as some alpha. So, that is non-dimensional regular solution parameter times x into 1 minus x plus. Okay. So, let me call this entire expression as delta h. So, in Octave script, for example, I will refer to this as dh. Similarly, this is x ln x plus 1 minus x ln 1 minus x, and this expression, as I did earlier, I am going to call as ds this time to distinguish it between. This is dg, delta g by RT is what I will call as dg. So, this is dh, this is ds. So, I am going to do these two calculations, and we are going to assume different alpha parameters. And remember, alpha, because it is defined as omega by RT, is inversely proportional to temperature, which means what? Smaller values alpha refer to higher temperature, higher values alpha means lower temperature. This is very important, because as you remember, at higher temperatures it is always this quantity which is dominant, which means alpha will become smaller and smaller. So, relatively that contribution is going to become smaller and smaller, and then this quantity will dominate. As alpha becomes larger and larger, that means the enthalpy contribution becomes important, that means we are at lower temperatures. Okay. So, we are going to use different alpha values, but remember, alpha is a non-dimensional scaled sort of regular solution parameter. Okay. So, that is what we are going to deal with. So, let us take the case. So, let us again go back to Octave and try to calculate these quantities and try to plot it and see how it looks. Okay. So, first I am going to clear everything that I have. Okay. And clear is for clearing all the variables that I have. So, if I now ask x, it will say that it is undefined. CLF is to clear the figure. Okay. So, it shows you an empty page for the figure. Okay. So, we are going to use this. Let me define x. Again, I am going to define it between 0.001 and it is going to increase in steps of 0.001. Let us go up to 0.999. Okay. So, that is the x value. The ds value, which is the non-dimensionalized entropy of mixing part, we are going to calculate as we did last time, x dot star logarithm of x dot plus 1 dot minus x dot star logarithm of 1 dot minus x. Okay. So, this is the entropy of mixing non-dimensionalized, that is why there is no RT term. Okay. We are going to calculate the h term, that is nothing but alpha. Okay. So, let me define alpha first. Let us define alpha to be equal to say 0.1. Okay. Now, dh is equal to alpha dot star x, it is x into 1 minus x, right. So, that is dh. Okay. Now, I am going to plot what are the things I am going to plot? I am going to plot x delta H, x delta S, then I am going to plot x dH plus ds, right. So, alpha is positive, which means this is a system that will undergo phase separation, but alpha is 0.1, which is a very small number, which means compared to omega the RT is very high. So, the ratio is 0.1 and so it is going to be dominated by temperature. So, let us see what the figure looks like. So, as you can see, so you have this quantity positive, that what you see above there in blue line is the delta H, because delta H is positive, remember. So, it will be above 0. The other line that you see is the entropy line, that is the green line, that is the one which is the lowest. But to this negative quantity you are adding this positive quantity. So, the red line that you finally see is the non-dimensionalized free energy for this regular solution. Okay. So, now what we are going to do is that let us go change the alpha value. Let us change the alpha value to be equal to some 1.5, right, and let us redefine dH. Now, let us plot. So, what do we get? Well, obviously, we have made larger contribution to enthalpy. Remember, we said that this is higher temperature, the lower temperature, because higher alpha value, and so the entropy had this negative value, but compared to that this quantity is comparable, right. So, this is going from somewhere 0.6, 0.7, and you can see already we are having 0.2. So, if you add it, then you get the red line, that is the total free energy. Let us go to still lower temperatures. How do I go to lower temperatures? I increase the alpha value. So, let me make the alpha value to be equal to say 2.5. I calculate dH, I plot these quantities. Now, how does the curve look? Interesting things start happening, right. So, this delta H is comparable to the delta S that we have. So, when you add them up at these two extreme points, you can still see that the entropy has the say. So, it still goes like that in the same way as entropy, but somewhere in between you can see that this quantity is having a curvature which is like this, not like this, right. So, this becomes much more prominent. Of course, there are two ways of seeing it. One is just plotting x and the overall free energy. Okay. So, you can see that, right. So, it has developed this kind of. So, the curvature on this side and on this side is like the ds curve, which went something like this, and the curvature in the middle is like delta H, which had a curvature like that. So, in between obviously it is going to develop these two well states. Remember, and these two wells are the ones, I mean, if you draw a common tangent, then those points where the common tangents touch are the points which are going to determine what the phase diagram is going to look like. Okay. So, this is one way of saying that. There is also another way, of course, we can do that by going to really low temperature. Okay. So, let us go to some temperature non-dimensional inverse temperature, right. This is inverse of temperature, alpha of some 4.5. Then what happens? So, I calculate dH, then I plot the quantity. You will see the unmistakable the majority of the portion of this overall free energy curve has a curvature which is similar to delta H. Very small regions at the extreme has curvature like the entropy. So, again, to see it clearly, let us just plot the overall free energy of mixing. You can see that at these extreme points is where you see a curvature which is looking like that of the entropy. So, it is like this and it is like this. So, this part if you extend, you will see a curvature that is looking like that, but majority of it is because alpha is very high, which means I mean for example, omega as compared to RT, the temperature at which you are looking at as compared to omega, that ratio is like 4.5. RT 4.5 times, if you multiply you get to omega. So, that is the kind of omega we are looking at. So, obviously, omega is dominating. So, this is very, very low temperature. But this kind of behavior where entropy is going to dominate is never going to disappear, except at absolute 0, when the entropy contribution is not there at all. That is because the entropy is calculated using the configurational argument. The configurational argument says that I replace some B atoms or A atoms by the other type. If I have, say, pure A or pure B, which is what these two extremes correspond to, and if I take very small number of atoms of other type, suppose I take pure A and then I have pure A, there is only one configuration, but the moment I introduced one B atom into this pure A, then if there are some n number of sites, then there are n different configurations. So, that much will be the increase in entropy. In other words, as you go to the purer and purer systems, the entropy, configurational entropy contribution is going to increase exponentially, right. So, it is a very large number, and towards a purer component it is going to increase very steeply, and that is the reason why there will always be this dominance at the end points of the effect of entropy. But other places, once you are beyond that point, the rate of change of entropy is not going to be very large with composition. So, exponential is not the right way of describing it. The right way to describe is that rate of change of entropy with composition, when you are moving towards the purer components, is very high. As you move away from near pure compositions, the rate of change of entropy is not that high. So, that the contribution from that part of entropy starts coming down. So, the end points will always be like this, but otherwise you will see the free energy coming like this. So, the free energy curve, it actually joins the y axis parallel to y axis. Okay. So, if you try to take the slope at these two extreme points, that is like infinity, and that is why we skip them while plotting, because that will give you not a number. So, that is going to join like with infinite slope. Okay. So, this is with respect to different alpha values, how the regular solution free energy of mixing looks like. Let us try to do it a little bit more nicely. Okay. And for that, what I want to do is the following. So, I want to take a few alpha values, and I want to plot the regular solution free energy for few different alphas and see how the curve looks like. This is the kind of curve that you might have seen in any thermodynamic textbook, like Gaskell for example, but we are going to produce it in octave and see how the curve looks. The curve looks very, very nice. So, let us try to do that in octave. So, how are we going to do that? So, let me take, I am going to define a function. Okay, function definitions we have not done till now. So, I am going to now define a function. The way function definition is done is as follows. So, I am going to define this function called y, which is a function of composition and alpha, right, because the free energy depends on composition and alpha. So, let me define function. The function return value is y. Y is nothing but a function of x and a. Okay. So, before that, let me first do the clear operation. Let me clear everything. Okay. So, then I say function. So, let me define this function. Y is equal to g of x comma a. Okay. Now, it wants to know what the function is. Y is equal to a dot star x dot star 1 dot minus x, right. So, a is nothing but the alpha that we defined, and this is the dh part that we are writing of the free energy function. Then dot plus the entropy part, that is x dot star logarithm of x dot plus 1 dot minus x dot star 1 dot minus x, right. So, this is the expression. I am going to put the colon here, because when this function is evaluated, I do not want anything to be printed onto the screen. Like I said, if you want to suppress any printing to the screen, you should put the colon at the end, semicolon at the end. So, that is what I have done. So, I am going to say okay, now I have defined my function. So, end function. Okay. So, this is an important syntax that you should know how to define functions. You can define, so I have defined a function and it has a return value y, and I called it as g because that is the free energy function, and it depends on composition x and the alpha parameter, which I decided to call a because I do not want to be writing alpha every time, and I have defined the functional expression. So, I have given the expression and you say end function. So, this is how functions are defined. So, defining functions becomes very important if you want to do lots of computations, and so this is a way of defining functions. There is also a way of inlining functions which we have done. Probably I did not say that I am inlining a function or something, but we will see more examples of that type later also. So, this is the function. Now, I am going to introduce a command called hold on. When you say hold on, what happens is that the plot that you have made is going to be kept, and in the same plot the next one will also be plotted, right. So, it is going to keep this same figure and it is going to keep plotting everything that I ask it to plot in the same one. So, this is a way of getting more than one figure. We have seen the other examples, right. You can say plot x comma y comma x comma z comma x comma a, whatever. So, for each pair it will plot one curve and they will all appear in the same figure. Now, here is another way of getting all the plots in the same figure, that is by using what is known as hold on, which means keep this whatever figure and keep plotting everything that I ask you to plot on the same figure. That is what hold on does, and so I have introduced hold on here. Of course, we define x. Okay, so let us go define x equal to 0.001, 001 and 0.999, right. So, this is what x goes. Okay. So, now I am going to say a is equal to 1.0. So, let us start with a is equal to 1, the alpha equal to 1, and then I am going to introduce the other command, which is the for loop. So, I want to calculate the x and the g for different alpha, right. Remember, each x and each g corresponding to that x is basically a vector, right. So, what I am going to do? I am going to use 4 different alpha values. The first one is alpha is equal to 1. Now, with alpha is equal to 1, so I am going to say for I is equal to 1 to 4, I is equal to 1 to 4, okay. A is equal to a plus 1, okay. Plot x comma g of x comma a. Remember, it is going to change alpha, and for each alpha value it is going to plot this curve once, okay. Plot g of x comma a, and then we are still inside the for loop. So, what is the last command? I say end for, okay. So, let us go look at the figure. Okay. So, there is something wrong. Yeah. So, I know what the error is. The function I defined, it is 1 minus x times logarithm of 1 minus x. So, I missed the logarithm. So, let us go back and redo, okay, and let us define. So, before that let me do a clear. So, let us see, clear only clears it from the memory of octave, from its working memory. The commands that you gave are still remembered. So, you can still access those commands using the up key. Okay. So, function y, and what does the function is like? This time I should not make this mistake. So, it is logarithm of this, and then I end function. Okay. So, then I do the other thing. What did I do? So, I need to define, I need to say hold on, but before doing that I have to clear function. Otherwise, whatever plot it had earlier, it is going to keep plotting on the same one. Okay. So, I just want to start with a empty page. So, CLF and then hold on. So, it is always a good idea if you are going to introduce commands like hold on, when you start any new script, the first line to be CLF and the second line to be clear and then start. Because if you are running the script and if Octave has already run something, so it will remember all those values and sometimes they can interfere with your calculation. So, it is always a good idea to start your scripts with clear and CLF. Okay. So, CLF then hold on. Okay. So, it starts with a new one. So, I am good 0.001, 0.001, sorry 0.999, right. So, this is the x. So, I am going to say A is equal to 1, right, for I is equal to 1 to 4, okay. I want to say A is equal to A plus 1. In fact, we can put A equal to A plus 1 after plotting, okay. So, we will plot for A equal to 1 also. So, plot x comma g of x comma A, okay. A is equal to A plus 1. So, next plot when it comes, A will be 2, A will be 3, A will be 4 and so on, and then say end for, okay. So, this is the interactive mode. So, I gave the commands and it executed everything and it must be having the figure, and you can see the figure. This is the kind of figure that you will get to see. Of course, everything now is in blue because every curve is plotted once. So, it takes a value of 1, it will plot, take a value of 2, it will plot, it will take a value of 3, it will plot, it will take a value of 4, it will plot. When you plot like x comma g of x comma A1 and x comma g of x comma 2, then there is a first plot which will be blue, second plot which will be green, third plot which will be red and so on and so forth. So, there are advantages to doing it that way, but here also there are ways of making sure that you have a legend which says what is what and then getting. Of course, in this case we know that the A equal to 1 is the high temperature one because that is low alpha. So, that is like this, and as you reduce the temperature you start developing these minima, and as you are going to lower and lower temperature, the minima is going towards purer and purer compositions, because that is how the the phase diagram look. You remember, if you go to very low temperature, the phase diagram boundaries are closer to the end compositions. As you come to higher and higher temperatures, so the phase diagram, so it is like a parabola, it is somewhere about 0.5 is where its top point is. So, as you go to higher and higher temperature, these points come closer and closer together, and at some point they merge and the 0.5 becomes a point at which they have the same value. Above that, the curve becomes like this, the curve becomes the same as the entropy curve, which means there is no longer any two phase region. So, this is the kind of curve that you would have seen in materials thermodynamics courses. For example, you can go and take a look at Gaskell's textbook, the regular solution chapter, in which you will see something like this, and they will show you that there is this critical point about 2 for omega by RT value, and below that you will have this two phase region, above that you will have a single phase region. So, that is basically the same information that we are showing, but here we are showing it in terms of the normalized free energy versus composition. Okay. Of course, the next step is to construct the phase diagram itself using the regular solution free energy. So, which is what we will do in the next part of this lecture. Thank you.